Andrew Dzurak, we are so excited to have you here at the Quantum Machines booth at the American Physical Society Summit here in Anaheim, California. You just did a live demo of your qubit device linked to Sydney, but showed it off here at the APS March meeting. What was it you showed us before?
Well, it was our team, Arne Laut, who's one of our most senior technical leaders, together with one of our PhD students, Paul Steinacker. And they were operating remotely, Paul was operating remotely, a 2-qubit device that was in one of our partner labs in Sydney. And this device is a CMOS-based multi-quantum bit device, and the team were demonstrating 2-qubit operations in this device. In particular, they were controlling each of the 2 qubits. They were initializing the qubit states. So our quantum bits are single electrons or groups of electrons to create a spin 1/2 state. And so our quantum bit basis states are either spin down or spin up in a magnetic field. And so what Paul was doing with our double quantum dot device was initializing the qubits in an initial state and then performing spin rotations on individual qubits. And also they were studying the interaction between the spins by raising and lowering a potential barrier between them, which is done with an electrode on the device, the CMOS device, and essentially increasing and decreasing the coupling between the 2 qubits, which is the way that we turn on and off the 2 qubit interactions. And so the team were using OPX 1000 Quantum Machines systems, which is really vital in order to optimize the initialization. Because when we initialize, we want to start with both of our spins down in a known state. But sometimes when we go through the initialization process, errors can occur. So you can initialize, for example, an up-down. And so what our team has developed, but using the OPX system, is very, very fast feedback, where we do an initial look at what the 2-qubit state is. And if it's not in the correct state, it goes back, does another loop, and does a rotation to get it into the correct state.
Kind of very simple error correction.
Correct.
Done with Quantum Machines OPX 1000 equipment.
That's right.
To get the qubit initialized super fast. And everything worked out during this live demo. A little daring to do it live at a big show like this, but it worked out.
It's the first time we've ever done anything like this live. And in fact, firstly, I actually, my team didn't tell me just how live that was going to be.
Yes.
So when I saw it happening, I was a little bit scared for having it, but it was perfect, as you saw.
Everything worked.
And the fidelities were extremely high.
Beautiful data.
It was beautiful data. The other thing that's kind of funny or scary is that my team also told me 3 minutes before we kicked off that last night in Sydney, there was a power cut in our partner's lab,
that can happen.
Which brought the fridge down, and so the whole system was brought up just in the last couple of hours. So, despite all of that, the fact that it all went so smoothly, we're really delighted.
Well done by everybody.
Amazing team.
And the special thing about Diraq's technology is that it's done with CMOS, right? So 300 millimeter CMOS wafers done using normal CMOS technology, and you make qubits out of that.
That's right.
What's so special about that?
So the special thing about it is that with our quantum bits are just modified CMOS MOSFET transistors. They have all the same materials.
Same as normal microchips.
Exactly right.
So normal computer chips, basically.
Exactly right. And so because the size of our quantum bits are pretty much the same as the size of transistors, actually transistors from a couple of generations ago, you got spacings of tens of nanometers, that means that we can put many hundreds of millions of qubits on a chip, right? Because of course we know that a modern computer chip has 100 billion transistors.
Yes.
Okay, so we don't go quite that as dense, but we can put hundreds of millions of qubits on a chip. And the important thing about that is that then in one single small cryogenic system, we can make a fault-tolerant utility-scale quantum computer that can solve all of those exciting problems like molecular design, pharmaceutical design, financial analysis, and so on.
Because we really need millions of qubits to get to full utility scale to get to the really important applications.
We do.
Yes.
Absolutely we do. And it's not just about getting a system with millions of qubits. You want to have a system that you can afford.
Yes.
Okay. And so we're looking at a system that will be compact. It will have low power consumption. In fact, we're looking at lower power consumption than GPU clusters that are used for AI.
Yes.
Our quantum computers will actually be incredibly energy efficient, and in terms of their overall production costs, quite economical. So what we're looking to do with our Dzurak quantum computers is to have hundreds of them in a data center,
Yes.
all performing calculations, different parts of a calculation in parallel, in partnership with advanced AI and classical compute. And this is really only possible because of the ability to integrate so many qubits in such a compact module.
Very important.
Yes.
And I mean, quantum computers are probably never going to stand alone. They're always going to be linked with normal supercomputing. Quantum computing is a kind of supercomputing, but normal supercomputers from, for example, Nvidia are still going to be very relevant.
Absolutely.
And at Quantum Machines, we have developed technology so you can link quantum computers to classical Nvidia supercomputers via the DGX Quantum system.
Mm-hmm.
And you're one of our first customers to actually utilize that.
Exactly.
What are your plans with that?
Yeah. So what that's going to allow is incredibly fast classical processing of the data that is coming off our qubits.
Yes.
That is going to be done with the Grace Hopper chip, the Nvidia Grace Hopper chip, the most powerful AI chip known to mankind.
Yes.
And that is then going to we're going to use the information to feed back information to get the optimal performance out of our qubits. Okay. So this ability in real time to do very, very fast
in just
data
a few
transfer,
microseconds. Right?
That's right. That's right. It's incredible. I should mention that the demo that we did today is already using very, very fast feedback from your existing OPX systems. In fact, one thing I didn't mention about one of the great things about silicon qubits is they operate at a temperature which is 1 Kelvin, which is very cold by what most people are used to. But actually at that temperature, you can run conventional chip electronics together with the quantum bits. And that operation at 1 Kelvin for us was only made possible because of quantum machines. So we published a paper in Nature last year in 2024 where we demonstrated extremely high accuracy or high fidelity qubits. And that was done by doing this correction that we showed in the live demo.
The very fast error correction.
Only possible with
because
quantum
most
machines.
other qubit systems, they have to run at 10 millikelvin, which is 100 times colder than 1 Kelvin, even
That's
though
right.
1 Kelvin is very cold. So being able to do that at 1 Kelvin is much cheaper from a cooling perspective, much simpler.
The main advantage actually, Jonathan, is that at millikelvin, if you put conventional classical electronics down and you try to integrate, those chips generate so much heat that they heat the qubit up.
Yes.
Up to a few Kelvin. When you operate at the Kelvin range, you can have the two fully tightly integrated. Otherwise, you have to run your classical electronics here, and then you have to run millions of cables down, which of course is infeasible.
Yes.
So that operation at 1 Kelvin is really crucial.
Really
and in fact, as I was saying, the work that we did together with Quantum Machines to optimize this fidelity using the fast feedback was crucial. And we foresee further improvements when we're, for example, using the Nvidia DGX Quantum system.
That's very exciting. And most of the work you've done so far has been in Sydney, Australia.
That's right.
But you're becoming a multinational company.
We are.
You're moving some of your operations to Silicon Valley.
Correct.
Yes.
So we incorporated in the United States at the end of last year. We've already hired some initial staff. We're looking to expand that team over the coming months. We see the United States as a core partner for Dzurak. I should say that, I've been a professor at our university in Sydney, University of New South Wales, for over 20 years, developed all of the silicon qubit technology that is now being used by Dzurak. And we have an amazing ecosystem, a big talent pipeline. But we actually have relied on very strong support from the US government through that whole 20 years. So we've always had very close relationships with the United States. And Australia and the United States have very, very close links across many areas of technology and even national security. And because quantum computing has applications across commerce, but also national security areas, the United States is a very natural partner for Australia, which is one of the reasons that we're setting up here in the US and expanding the team. So we're going to have test labs here in the United States. We're going to have chip design teams and so on, and of course sales teams when we start rolling out our first systems.
Extremely exciting.
It is, Jonathan, and thank you to Quantum Machines to help us make all this possible.
Well, thank you for doing this together with us. We're going to change the world, I think.
Absolutely.
Yes.
Pleasure.
Great, thanks.
Thank you.